All right, let's go ahead and get started. Hello, everyone. Welcome to SECOORA's first webinar of 2018. We are hosting this webinar series, Coastal Observing in Your Community, to discuss, highlight, and raise awareness about coastal ocean observing in the Southeast U.S. My name is Abby Wakely, SECOORA's Communications Director, and I will be facilitating and moderating the webinar. All participants will be in listen-only mode. You are encouraged to type questions for the presenter or technical questions in the bottom left-hand chat box. I will respond to them directly or post the questions to our presenter after his presentation. We are recording this webinar today and will be posting the recording along with the PDF of the presentation on the SECOORA website. We are very, very excited to welcome Dr. Bob Weisberg from University of South Florida College of Marine Science as our speaker today. He will be presenting West Florida Shelf and Tampa Bay responses to Hurricane Irma, what happened and why. Dr. Robert Weisberg is a distinguished university professor of physical oceanography at the University of South Florida. His current research emphasizes the West Florida continental shelf and the interactions occurring between the shelf and the deep ocean and between the shelf and the estuaries. He maintains a coordinated program of in situ observations, analysis, and numerical circulation models aimed at describing and understanding the processes that determine the West Florida continental shelf water properties with applications to matters of societal concern. Dr. Weisberg is on the board of directors for SECOORA and is a fellow of the Southeastern Universities Research Association. Dr. Weisberg, thank you so much for joining us. You can go ahead and share your screen. And I apologize for the beeps. I have not figured out a way to turn those off. And I am seeing your screen, Bob.
Okay. So I'll begin, and I want to thank all of you for sharing your lunch hour with me. Let me first discuss a little bit about what SECOORA is, what all those acronyms are that you see on the top of the first slide. So SECOORA is the Southeast Coastal Ocean Observing Regional Association. It's a bunch of people that are interested in developing environmental intelligence for the coastal ocean. There are lots of applications of a societal nature. I'll discuss some of those today. SECOORA receives its funding from NOAA IUS. IUS is the Integrated Ocean Observing System. It's really an international effort. In the United States, we have 11 of these regional associations like SECOORA. So it's people like me that are attempting to make observations in the coastal ocean and figure out how the coastal ocean works. On the west coast of Florida, we started with a program called COMPS, Coastal Ocean Monitoring and Prediction System. We started doing this in 1998 with some assistance from the state of Florida. The idea is to make long-term observations of anything in the coastal ocean. We started with physical oceanography, how the water moves around, because frankly, everything else is dependent upon that. The Earth's climate is dependent upon the ocean circulation. The Earth's ecology begins with the ocean circulation. That's what unites nutrients with light. That's what determines the water properties in which all the critters live. In fact, I like to say that habitat has two aspects to it. One is the static part, the shelter, the rocks, whatever the animals live in. The other are the water properties in which the animals live. And so I like to say that, as an example, why do snowbirds come to Florida? Well, they really don't come for the terrain. It's kind of boring. It's flat. If they wanted terrain, they'd go to Hawaii, they'd go to Iceland. Both places are beautiful. They come to Florida because it's warm. It's got a pleasant climate. Well, why does that happen? Because the air is driven by the atmosphere and the winds, and that determines the temperature. So it's not the rocks on the ground that bring the snowbirds to Florida. It's the dynamical aspects of habitat that do that. So to the ocean, that's why we study the ocean circulation. And what I'm going to do today is talk about the West Florida Shelf, so it's the coastal ocean adjacent to West Florida, and the Tampa Bay responses to Hurricane Irma, what happened and why. And I'm also going to introduce you to certain tools that we have developed on the West Florida Shelf and for Tampa Bay, and discuss the potential for other interactions that may be of interest to you. So I'm presenting my associate Yonggang Liu has played a major role in this, and my graduate student Jing Chen has similarly played a major role in this. And at the end, I'll acknowledge some other contributors. So here we go. So my group is called the Ocean Circulation Group. We're in the College of Marine Science at USF, and we maintain a coordinated program of ocean observing and modeling with a concentration on the West Florida Shelf and Tampa Bay. During Irma, we deployed 3 real-time buoys along with various coastal stations and circulation models for both the West Florida Shelf and Tampa Bay provided information throughout the storm. There's an example of a buoy in the lower left. The model we call our West Florida Coastal Ocean model, which consists of an unstructured grid model nested in what's called the Gulf of Mexico HYCOM, which is a model that covers the entire Gulf of Mexico run by the Navy. So we get our open or deep ocean conditions from HYCOM, and then we downscale that across the shelf and into the major estuaries. For want of a little more resolution is very important, as you'll see. We actually have a separate model for Tampa Bay. We call that our Tampa Bay Coastal Ocean model, and it further nests this unstructured FVCOM into our West Florida Coastal Ocean model. So we go down to resolution as fine as 20 meters, resolving the main shipping channel, the Intracoastal Waterway, Sarasota Bay, the detailed configuration of the upper reaches of the rivers, and all of the inlets that connect this region with the adjacent Gulf of Mexico. And for certain problems, it's very important to have that resolution. All right, let's talk about Hurricane Irma. So here is a rendition from NOAA's global forecast system. It's their analysis at 0-100 UT on September 11th, 17. And you can see where it says low, that's the hurricane, that's Irma, just as it was halfway between Naples, Florida, and the Tampa Bay vicinity. The color coding on the right is wind speed in knots. 64 knots is a hurricane. And so Irma at that time had winds just about hurricane strength. It was probably a Category 1 hurricane at that point. The claim is it made landfall as a Category 3 or 4, and then it decreased to a Category 2 at its second landfall at Naples, and by the time it got up to the Tampa Bay region, fortunately it was greatly reduced in magnitude. So there's the hurricane in the context of the larger scale wind field. At that time, we had several different types of instrumentation. It consisted of surface buoys with real-time ocean and meteorological sensors. There were 3 of them, C10, 12, and 13, as you see. We had some high-frequency radars that sample surface currents, and there were a bunch of coastal stations distributed from the Keys right up to Panama City, and those coastal stations were operated either by the COMPS program or by NOAA, NDBC, or NOS. The COMPS stations, tide gauge stations, are operated by my colleague Mark Luther at USF. I'm going to show you data from the ocean. I'm not going to show HF radar data today. During the hurricane, we were a little disappointed with the radar coverage, which I'm still trying to figure out because in non-hurricane settings, they generally work pretty good. But we had some limited coverage during the hurricane, and once power went out, we had no coverage. So that probably had a lot to do with it. In the right, you can see the track of the storm where it made its first landfall at Big Pine Key, Cudjoe Key, did a lot of damage there. Second landfall at Naples, and it was pretty far inland by the time it passed here. So that really saved us. We really lucked out, as you're gonna see. All right, so let's begin by looking at what the surface wind field looked like as the storm moved from south to north. Those are the purple vectors in these plots. What the coastal ocean response, as simulated with our West Florida coastal ocean model, looked like. So the black arrows are the surface currents, and the color coding is sea level. If we begin in the upper left, you can see that the storm was south of the Keys, right around here. It was working its way to the north. The winds in Florida Bay were directed offshore, so you can see that sea level in Florida Bay was starting to go down. You can see the direction of the surface currents at that time. And sea level along the Florida Keys was going up, the storm surge in the Florida Keys, and it set down on the other side. If we look 11 hours later at noon UT on the 10th of July, the storm was just about ready to make landfall. Sea level was dropping very rapidly in Florida Bay. The region that's white is dry. And so this model does have the capability of flooding and drying land, which is critical for any storm surge model or any estuarine model, for reasons I'll go into later. So you can see a good portion of Florida Bay was already drained of water. The fish were all flopping around on the bottom. But fortunately for the fish, a couple hours later, the storm moved north and sea level started to fill in very rapidly within Florida Bay. You can see a surge happening here. And then as the storm was just north of Naples, now we had a nice storm surge in Florida Bay and a drawdown of water in Charlotte Harbor and Tampa Bay. So the way the sea surface responds and the ocean currents responds is very dependent upon the winds that are blowing locally at that time. So a couple hours later, at 4 UTC on the 11th, you can now see all this drying of the ocean in the Florida Big Bend region. Tampa Bay was pretty much drained of water in its upper reaches. And yet down here we had the surge starting to fill in. 4 hours later, you can see the draining of water is moving to the north. Charlotte Harbor now has a surge. In Tampa Bay, it's starting to form a surge. And 4 hours later, you can see how this is all evolving. So now, by the 11th of September, so a day after Tampa Bay drained out, you can see that the water filled in pretty quickly. And then later on that day, as the storm made its way north out of Florida, sea level is starting to return to normal. So the evolution of the sea level changes and the current changes are all moving very rapidly as the winds are evolving. So that's basically how the storm went through our region and what the winds were like as it went through our region. So how did we do with the West Florida Coastal Ocean model in modeling the storm surge? In the right-hand panel, you see a map showing a bunch of tide gauge locations from Key West to Sea to Key. And then the left, we compare the observed sea level with what we modeled with our West Florida Coastal Ocean model, which is being driven by NOAA forecast winds. The first thing you see is that in some locations we did actually very well. In other locations, like at Cudjoe Key, our model simulation bottomed out long before sea level bottomed out. In other words, we put our tide gauge in the model in the wrong place, which is another reason why very high resolution is extremely important, because in nature, you have an observation, a real observation at a certain point in space. In a model, well, you're limited by the resolution of the model and also how well your bathymetry is. So at Cudjoe Key, at least in this rendition of our West Florida Coastal Ocean model, we sampled the sea level in the wrong place relative to where the tide gauge actually was, and where we sampled it, we didn't have the water depth deep enough. Otherwise, we would have matched Cudjoe Key pretty well. Because at Clearwater, you can see we did match sea level very, very well. McKay Bay, which is the northern reach of Tampa Bay, again, in the West Florida Coastal Ocean model, whose resolution up there is only about 300 meters, we sampled the wrong place, so we didn't get the full drop in sea level. And so you can go down the list and see that the model worked pretty good. Where it didn't work, our resolution probably wasn't high enough, and maybe the winds weren't quite right, which I'm going to show shortly. At our buoys, we measure both surface meteorological variables as well as in-water variables. And so what you're looking at is the location of those buoys offshore, a picture of what a typical buoy looks like, and below that picture of the buoy is some wave data that I just received today, courtesy of the group at Scripps that runs the CDIP array. And during the storm, as the storm went by, we had greater than 6 meter significant wave height. That's about 14 feet of wave height. That buoy is only 6 feet tall, so you can imagine it got beat up pretty well. When the significant wave height is 6 feet, the maximum wave height is usually twice that amount. So we had, I meant to say meters. We had 12-meter waves, or about 38-foot waves out there, monsters. And so it's no wonder that when you look at the time series at C13, you can see that the winds kind of petered out as the storm went by. We still had temperature data reporting for a while, but what happened at C13 is our power system got literally knocked off the buoy. So the solar panel went away and the battery went away, and probably at some point our antennas went away, and so we stopped receiving real-time data. At C12 it lasted a little bit longer, same thing at C10, except at a certain point the power system also got damaged, so once we ran out of power, both of those buoys went down a couple of days later, and we had to go out and repair C10 and 12. We've had neither the resources nor the time to go out to C13 yet. The buoy's still there. The buoy survived just fine. Just the power system and some of the sensors were damaged. One thing I want you to look at is the temperature record from these buoys. At C10, temperature dropped a little bit, but the offshore buoys, the temperature dropped quite a bit, up to 4 degrees centigrade. That was by a combination of upwelling that I'll show you and mixing. The reason why C10 didn't drop more is the water column was fairly well mixed to begin with, and so we didn't have that colder water near the bottom to come up to the surface. So this is the type of meteorological data we have. It's very important for forecasters at NOAA to assimilate these data into their models. and we're trying to maintain an array like this and add to it going forward into the future. We also get shortwave radiation and incoming long-wave radiation, so we can do complete heat budget studies of the near-surface waters to account for why temperature changes the way it changes. So let's look at what happened across the water column. So these are C13 winds, and this is the along shelf component of current measured at C13. I'm sorry, the across shelf component and the along shelf. Red means the water is flowing toward the coastline, blue away from the coastline. So as the storm passed, we were in this tremendous upwelling environment where surface water is moving offshore, bottom water is moving onshore, sea level is dropping, and the alongshore current was very strong, in this case to the south, flowing at about 1.5 knots. Then as the storm passed, we get a reversal to a downwelling situation where now water is flowing back toward the coastline, causing sea level to rise. So it's the movement of the water offshore that determines the up and down motion of the sea level along the coastline. And by having buoys out there and models, we can begin to develop a much better understanding for why we get these coastal depressions and surges as the storm goes by. You can see that while the winds went out sooner, the currents lasted longer. In fact, I wouldn't be surprised if C13 is still recording currents. We just lost our telemetry because the power system went down. When we go recover, we'll know that. If we look at C12, a similar rendition here, and C10, we see that, again, we had this very strong upwelling response, offshore flow at the surface, onshore flow at the bottom, a very strong along shelf flow as the storm was passing by, and then that changed to downwelling. We see the same thing in shallow water, except now in the shallower water, instead of seeing that bipolar nature of the flow, one way at the top, another way at the bottom, you can see it's more unidirectional top to bottom as that water very quickly flowed away from the coast and then back toward the coast. And we can compare the observations of the currents with the simulation of the currents, which is what these three sets of plots do. On the left-hand panel, we have mooring C10 on the 25-meter isobath, C12 and C13, two different locations along the 50-meter isobath. The top set of time series compare the simulated currents with the observed currents. So this is time, and this is magnitude, and each one of these lines is a vector. So the current is flowing from here to here. And if we look at the magnitudes at the surface, observed and modeled, we see that the model slightly overestimated the observation at all depths. But the character of the flow is generally pretty good. So the model worked well, it just overestimated the currents by a little bit at these locations. This is interesting because typically the model is underestimating the currents during a typical wind event. During a hurricane, overestimating the currents. What that tells us is that the winds that we used to drive the simulation were overestimated. So the forecast winds were larger than the actual winds. We were overestimating the intensity of the storm as it moved across the state of Florida. And so the lesson from that is, we actually need more observations at sea so that our forecast winds will be better, enabling us to have better forecast ocean currents. So the models work very well, except the magnitudes are off by a little bit. And there's a lesson there. All right, now let's zoom in on Florida Bay. Some very interesting things happened of ecological importance. So here's what our model grid looks like in Florida Bay. We designed it this way because it's important to get the inlets, the primary inlets, included in the model. So here's Key West. We know there's a nice deep channel here. Here's the Marquesas. Here's a big shoal, but there's a pass over here and another pass over here. And so we have to make sure we have those water depths approximately right and resolved so that we can get the flow fields correct to see how the Florida Straits are interacting with the much shallower West Florida shelf in Florida Bay. So I'm going to show some satellite imagery which shows some very interesting features. So here's a satellite image from the 11th, the 12th, and the 13th of September, and what you see is all of this sediment-laden water. And you also see sediments along here, along the reef track. And sometimes those sediments get entrained offshore. Sometimes you have these filaments moving. And in each one of these figures, the primary thing that stands out is there was a tremendous sediment load transferred from Florida Bay onto the reef track with very important ecological consequences. And then the question is, can we account for that with our West Florida coastal ocean model? The answer is yes. And so to demonstrate that, I'm showing the model surface velocity field. Those are the black arrows. And I'm showing drifter trajectories, simulated drifter trajectories. So where a water parcel would go as influenced by these velocity vectors that we modeled. Red is at the surface, blue is at the bottom, so we can track particles throughout the water column. And each one of these panels was initialized at 1 o'clock UTC on the 10th of September. This is 12 hours after initialization. So a particle that started here went over to here, and so on. Particle here went to here. This is 16 hours later, 20 hours later. So let's just look at the one 20 hours later. Particles that were on this side of the Keys ended up being on this side of the Keys. And so by having high enough resolution, we can actually track where the particles went, consequently where the sediments would go. And if we perform a similar operation the next day, you can also see very clearly that particles that were here went to here, and so on. And so we can account for the sediment-laden water that we saw in the satellite image on the basis of the simulations that we're able to do with the West Florida coastal ocean model. Well, the reef track is very important. So being able to figure out why the reef gets covered with sediment from time to time, or why very cold water might get ejected onto the reef track. By the way, the cold water can be as damaging to the reef track as warm water. So we attribute a lot of reef damage to warming temperatures, but on a really cold year, like occurred in 2010, we can really damage the reef track. And where does that cold water come from? It comes from Florida Bay. And so the ability to be able to account for the movement of water and the properties contained in that water is really critical to understanding the ecology of the reef track. So we now have a tool that enables us to do that. Let's move a little farther north now and take a look at Charlotte Harbor. In our West Florida coastal ocean model, we go down to 100-meter resolution in the Charlotte Harbor estuary. And then we can ask the question, when the estuary drained out where'd that water go? And so here's, again, like before, we initialized particles at 1 o'clock UTC on the 10th in all 3 panels. We looked 8 hours later, 16 hours later, and 20 hours later. The black lines are the surface currents. The blue and the red lines are where either surface or bottom particles got advected to. Well, anything in the water, sediments, the larvae, nutrients, etc., also got advected with the particles. And so you can see that all this water that drained out of the Charlotte Harbor estuary just went bye-bye to the south. That water did not come back. It was replaced by new water that came in from the north. So whenever we have a major event and water gets carried out of an estuary with whatever is contained with that water, it gets replaced by other water. In this case, it came from the north, not all the way from Tampa Bay, but at least from midway between Tampa Bay and Charlotte Harbor. So if we really want to understand what controls the water properties and therefore the ecology of the Charlotte Harbor estuary, we've got to understand the circulation. Well, let's move up to Tampa Bay. Here we felt, since we live here, we really wanted to have even higher resolution. The Tampa Bay system is a very complicated one. There's big, long barrier islands and Sarasota Bay and the Manatee River and Tampa Bay proper, and all the connections between these water bodies and the adjacent Gulf of Mexico. So we wanted to nest even a higher resolution model into our West Florida coastal ocean model. So remember that the West Florida coastal ocean model out here gets its open boundary values from the Navy's HYCOM. So the Gulf of Mexico impacts the West Florida shelf. The West Florida shelf in turn impacts the nearshore waters and Tampa Bay. And being able to do that properly is essential to understand the water properties and the ecology of Tampa Bay. So, as I said earlier, we resolved the shipping channel, we resolved the Intracoastal Waterway, and so on. So let's see how we did during Hurricane Irma. So here's our what we were able to model as the storm was passing through, because we got our winds from NOAA, we got our rivers from the USGS, and we run the model in a forecast mode. So this is what our initial result for Irma. We're looking at sea level at various stations: St. Petersburg, Clearwater, McKay Bay, Port Tampa, and Port Manatee. So different stations throughout the bay. The observation is blue, so that's what actually occurred. The model is red, that's what we simulated. And the tides alone, the predicted tides alone, are green. And so in advance of the storm, everything's kind of tracking together. Then the storm starts to come, and we see this emptying of water out of Tampa Bay at all of these stations. And our model, well, it was anemic. It underestimated that draining out of water. Well, why is that? Well, let's take a look at the winds used to force the model. So the observed winds at the stations where we had winds are shown in blue. The modeled winds that we get from NOAA, the NOAA forecast winds, are in red. And you notice two things. One, the forecast winds were in the vicinity of Tampa Bay itself, as the storm went by, were smaller than the observed winds, which is opposite from what happened offshore. Offshore, they were overestimates. In the bay, they were underestimates. and they're underestimates by a factor of 1.6 when we average over the passage of the storm. The other thing you notice is that while the winds that we observe are observed almost continuously, the winds that we get to force the model are every 6 hours. So the combination of the underestimated winds over Tampa Bay and the smoothing out by only having 6-hour samples from the model available to us caused the underestimate. All right, so we did one simple thing, and we did it one time. We didn't even experiment multiple times. We simply said, all right, the underestimate is by a factor of 1.6. Let's jack up the winds in the vicinity of Tampa Bay only by 1.6, and this is the result. So now we're spot on with the sea level throughout Tampa Bay. The lesson is modeling the coastal ocean response to winds requires more accurate winds. And this can only be achieved if there are enough coastal ocean wind observations to be assimilated into the weather forecast models. To me, that is probably the main justification for this entire IU's program. Why is that? Well, the ocean is driven largely by winds. The ecology is driven largely by the ocean circulation. If you want to get an improved ocean circulation, you improve winds. If you want to get improved ecological forecasting or even just ecological understanding, you've got to have the circulation correct. And so all these things are linked. From a NOAA perspective, and I know there's some NOAA people listening in today, from a NOAA perspective, you got the Weather Service, the Ocean Service, and the Fisheries Service. Well, the Ocean Service depends on the Weather Service, and the Fisheries Service depends on the Ocean Service. They're all connected, and the connection is, it all begins with the winds. And there are just insufficient winds observed in the coastal ocean to constrain the models well enough in the coastal ocean. And so when major events occur, we either get overestimates or underestimates, and that can be improved simply by having more judiciously placed wind observations, which is one thing that SECOORA and NOAA IUs is all about. So that's my plea. We need more observations. But given adequate observations and given the tools that are being developed, we can do an excellent job in both forecasting and hindcasting the response of the ocean, both along the coast and in the estuaries, to these major events. So here's how the currents and sea level evolved in the Tampa Bay model domain as the storm passed by. So on the left, you see the wind vectors as the storm was approaching the Tampa Bay vicinity. On the right, you see sea level, the color coding, and a bunch of surface velocity vectors, too many to look at, so don't look at it. Just look at the colors. And what I really want you to note is that we can dry out in the model the bay, which occurred. And so you can see all this drying around the periphery of Tampa Bay, and Boca Ciega Bay was basically all dry. And then as we go on in time, this was the period of time when sea level was set down by a maximum amount at St. Petersburg, at least. Again, you see all the drying. Particularly look in here. All this shallow water was basically emptied out. And that continued for a while until the winds changed direction, and then all of a sudden water surged right in. Well, why did the water surge right in? Well, you can see that if sea level has a certain level here and it's completely dry here, there's a pressure force that wants to drive fluid from here to here. There's a location along the Pinellas Beach is called Shell Key. It's a barrier island, and a new inlet was cut across Shell Key as Irma went by. Had that happen? Well, sea level was the ocean was dry on the inside of the barrier island. It was higher on the outside, and once those winds reversed and sent water flowing in, any breach of that barrier island would have been accompanied by a massive surge of water and waves driving fluid through that breach, which then just opened the breach up. The same thing happened during Charlie back in 2003. North Captiva Island opened up a new inlet at that point in time. In fact, if you look at most of the inlets along the west coast of Florida or up and down the east coast, most of those inlets were cut at one point or another by a major meteorological event, like a hurricane. John's Pass is attributed to the 1921 storm. So being able to resolve the currents and the sea level with a very high resolution model is necessary to really understand the coastal morphology. Just like for the Charlotte Harbor, you know, when the water left Tampa Bay, it went somewhere, and it didn't come back. So let's take a look at what happened to the water in Tampa Bay. You'll see this little red line over here. Everything to the northeast of it stayed in the bay. Everything to the southwest of it departed the bay. So each one of those dots is where we put a particle at the surface and the bottom. We trace those particles as they move. And this middle panel are for particles that were above this red line, and you can see none of those left the bay. And this right panel is for the particles that were down here. All of them left the bay. So water didn't flow out uniformly from everywhere. We can now see where the water left from and where it remained. And then when the water came back in, we can see where it came from. So actually most of the water that flowed back into Tampa Bay came from the vicinity of, the northern Pinellas beaches. And all of these particles farther offshore, they just kept flowing down the coastline. So it's important to know where the sources and sinks of both water and nutrients and larvae and whatever are with respect to Tampa Bay, and given a very high resolution model, we can begin to do that. You can't do it without such resolution, and also without the proper connections between the bay and the adjacent Gulf of Mexico. Okay, so I mentioned that this Tampa Bay coastal ocean model is now being run as a nowcast forecast model. Here are hourly snapshots at 3 different times from a couple of days ago. You can actually go to the website right now. I'll give you a link, and you can look at this in real time, and you can get a forecast for tomorrow and the next day if you'd like. But let's look in the left-hand panel. This is an outgoing tide, and a couple of things I want to point out. Notice how during the outgoing tide you have very strong currents flowing to the north, and they extend all the way up to past Pasadena, so up to Treasure Island. On the incoming tide, you have very strong currents flowing from north to south, and again they extend all the way up to Pasadena and St. Pete Beach. And this is just the next outgoing tide. The point I want to make here is that at the mouth of the bay, the currents are extremely complicated. And we know these are correct. I took a couple of days off 2 weeks ago and went sailing. And so the last leg was from here back to my house, which is somewhere back here. And so I went through this so-called swash channel. Either you can go through the swash channel, or you got to go way the hell out here because you have a big shoal on the north end of Pascagoula Channel. Well, why is it called the swash channel? Well, it's called the swash channel because it's kept clean by very strong currents. And here they are. So in my sail from here to here, there was a nice strong northeast wind. I was probably making 6 knots going across the lower part of the bay, even against the adverse current. But once I got to around here, all of a sudden the hull speed went down to like 3.5 knots. That current is very real, and I encounter it every time I sail out there on a incoming tide. And conversely, when you go out on an outgoing tide, you speed up. So if we have any interest in understanding the sediment budgets of this region, or any region around the mouth of Tampa Bay, we have to apply a model that is complete enough. So a model that actually gets not just what's happening in a small region locally, but what's driven by more far-field forcing. And there are some people on board today on this webinar from Pinellas County, and they know exactly what I'm talking about. And so if we want to understand our coastal morphology, we have to apply models that are complete enough to do that. And we now have such a tool that will enable us to do that, and I'm hoping that the general boating public will find this useful for their outings. I have a friend that likes to go paddle boarding. He's been wanting currents in the Intracoastal Waterway for a long time. He now has them. All right. There are a lot of applications that we could make with tools such as this. And so let's just talk about a few real fast. How about flushing of restricted water bodies? So what you're looking at is a study we did a couple of years ago looking at the residence time in Sarasota Bay, and we put a dye in the model and we watched that concentration change with time under the action of tides and winds. And what we found is that the lower portion of Sarasota Bay flushes very rapidly. Why? Because you got two adjoining inlets. There's a slight phase difference in the tides, and so when water's initially flowing in over here, it's flowing out there, and conversely. And so you can very rapidly flush that portion of Sarasota Bay, whereas this upper portion doesn't flush worth a damn. And so, again, being able to resolve the channels and to resolve the intricacies of the geometry are essential if one is to do any type of study like this. How about search and rescue? Let's take a look at the Courtney Campbell Causeway. You read in the newspaper every now and then a boating accident or a swimming accident. So where might a swimmer or a boater go according to the currents there? Well, again, we resolve these two different inlets so we can get the circulation correct in that very intricate area. We can also look at why you might get high nutrient concentrations here because the flushing is absolutely terrible. And we might do engineering studies of how we might improve flushing in here. So, but you can't do any of that without very high resolution. So for search and rescue, forensic studies, we need things like this. Years ago, there was a gruesome set of murders in Tampa Bay. The guy's name was Obed Chandler. You might remember that. He murdered 3 women. And we were called to figure out, well, where might the bodies have come from? Well, we needed tools like this. We didn't have those back then. We have them now. How about fish larvae studies? Well, spotted sea trout are known to spawn at Bunce's Pass, preferentially. Why is that? You know, somebody didn't tell them to do that, but they evolved that way because when you look at where the larvae might go after spawning at Bunce's Pass, they get distributed throughout regions that are covered by seagrass. They're settlement areas. And so they preferentially spawn there because that's where their settlement will be successful. And so we can do studies like this to look at fish larvae transport. How about harmful spill tracking? There was a sewage spill in Boca Ciega Bay back a while ago. This was last summer, but we had a simulation from 2001, so we were able to show where the sewage would go and how the concentration would change with time. So how long does it take to dissipate a major pollution event? And on the left-hand panel, you can see the currents, and you can see how by finally resolving all of these different channels, we can look at how water moves around. There's a new bridge that's about to be built over here. I would think that the DOT would be interested in having a chat with me about that, because this is the only model that actually has the ability to resolve finally the currents that are flowing through there. And that goes for all of the inlets. This is Blind Pass and Passerelle Inlet. So we actually have the tools now to do things like this. And as a final example, several years ago, it was actually in 2008, just before the real estate market crashed, there was a developer that wanted to cut some residential canals, and so we did a study looking at the flushing of those canals. Here we went down to 10-meter resolution, and this is right near the Gandy Bridge, and it's an insert in the entire Tampa Bay Westwater Shelf model. We were able to just insert this very finely into the larger scale model so that we're not just looking locally, we're looking at both the local impacts and the more distant impacts on the flushing of a very small region. Okay, so let me give a couple of conclusions. First, our West Florida coastal ocean model performed well for the Westwater Shelf response to Irma, including Florida Bay and the Charlotte Harbor Sanibel estuary. The higher resolution Tampa Bay coastal ocean model performed well for Tampa Bay during Irma, especially when the winds were corrected to match observations. And so the lesson is the observations are critical to model performance and veracity testing. And this provides, in my opinion at least, the strongest justification for an integrated ocean observing system and the direct coordination between observations and models. There's never enough observations. Models without observations, in my opinion, are useless. When you combine the two, you really start to learn things. Both the WFCOM and TBCOM are run as automated nowcast forecast models available to anybody. Given TBCOM and its WFCOM counterpart, we now have the capability to downscale all the way from the deep ocean across the shelf and into the estuaries, providing opportunity for multidisciplinary studies, which I welcome. So we're looking for partners for addressing matters of ecology, fisheries, sediment transport, emergency management, engineering, and forensic concern. And all of these applications begin with the circulation. If you don't have the circulation right, in my opinion, you can't do anything else. And we're also looking for ways to provide better information for use by the general public. And before I open up for questions, let me just make a couple of additional acknowledgments. My college for the COMPS program assistance, Pinellas County Restore Act funding for the Tampa Bay Coastal Ocean Model. Special thanks to my colleague Linian Zhang for WFCOM and his initial work on TBCOM. Linian was hijacked away by NOAA, and he's got an excellent position there, and we still interact. Jay Law for seagoing expertise, Cliff Murs for the HF radar, Dennis Mayer for analysis assistance, and Jeff Donovan for all aspects of the data and computer systems management. And of course, Abby Wakely for organizing this webinar series. And thank all of you for your attention. I'll try to answer questions you may have.
Great. Thanks so much, Bob. Thanks for the great presentation. Seeing that it's 3 minutes to 1, we're going to open it up for just a few questions. Please type your questions in the bottom left-hand chat box. If we do not get to them, we will make sure that you connect up with Dr. Weisberg and we'll share that information. And as I stated earlier, a recording of the webinar and a PDF of the slides will be available on the SECOORA website. So, Bob, I had a question from a fellow named Joe, and it was probably about 3 slides in. He had a question on your first description of the model. Was the model run of Irma's forecasted track in wind speed and size? Is that what you were comparing to? I thought it was comparison between the surface currents and the winds.
So, yeah, we were comparing, well, we drive the model with the surface winds, and so we're doing a comparison of the winds that we got from NOAA, which is what we used to drive the model, against the currents that we modeled and the sea level that we modeled. And so, you know, each is dependent upon the other.
Great, thank you.
So Bob, this is Jennifer. We have several questions from Mitch Roffer, and Mitch, I'm not certain if I'm going to get to all of them, but I'll try. Mitch is asking if you can estimate the amount of water quantitatively entering into the estuaries and also estimate the sea levels. If the answer is yes, what are the associated errors?
Okay, no, the answer is yes. I mean, we do have, and I haven't done that, but we do have actual sea level observations, so we can calculate volumetrically how much water left the bay, and then, of course, the bay eventually filled up again, so we can calculate that. The errors associated with that would be largely errors associated with our bathymetry, because that would determine the actual volume of water in the bay. I haven't done that, but it could be done. Now, from the model, since we know the model did duplicate the sea level response very well, we can go ahead at the mouth of the bay, either Charlotte Harbor or Tampa Bay, and calculate the flux of water that flowed out. So, yeah, we can do all that. I haven't done it.
All right, so we have a couple questions here from Mitch. The other is, do you have resources to study the inland sea level gauges to see the sea level effects of the storm inland and how long these effects lasted?
I think there are a bunch of gauges that the USGS maintains. I have not looked at those, but that's an interesting question. That's something we could take a look at. The model, I have to see just how far inland the model extends. In some places it extends pretty far, like the Manatee River. But I'd have to take a look at just how far up we go in the other rivers. It's something I haven't thought about doing yet. That's a good question, though.
For one final question, and this is, and I'm very sorry if I get your name incorrect, but I think it's Braulio Juarez. He wants to know if you've ever watched and compared the role of wind stress divergence and wind curl to enhance the surges.
That's a really good question. For the coastal ocean, the wind stress magnitude seems to be a little more important than the curl. And the curl of the wind stress is what drives the large-scale ocean circulation. But once we get into shallow water and there are coastal boundaries, the divergence of the water as driven by the wind stress is more important than the up and down motion as driven by the wind stress curl.
Great, thanks, Bob. And it seems to be right at 1 o'clock, and that is all of our questions. I did send the email in the left-hand chat box. It's weisberg@uss.edu. It's also on the website. And give us about 72 hours to post a recording of the presentation and a PDF of the presentation on SECOORA.org/webinar-series.
And if anybody is interested in following through, please send me an email, and I'll be happy to speak with you further about any of these topics. So thanks again for your attention.
Great. Thanks so much, Bob. And I do want to let you know we have another webinar Tuesday, February 27th, same time, 12 p.m. to 1 p.m. Eastern, and we're going to be discussing SECOORA's new data portal. And then I do also want to chime in that we have 2 student opportunities and new career development opportunities. So just let me know if you guys are interested, and we can send you that information. All right. Thanks, everybody, and thank you so much, Bob. This was a great presentation.
Thank you.
Have a great day.